It's like, why does math have to exist?
Okay.
That's the
fair question. Yeah. Okay. Fair question. Let's see. I think the thing to think about is the existence of mathematics is something where, given a definition of terms, what follows from that definition inevitably follows. So now you can say, why define any terms? But in a sense, that's okay. So the definition of terms, I mean, I think the way to think about this, let me see.
So like concrete terms.
Well, they're not very concrete. I mean, they're just things like, logical or
right. But that's a thing. That's a powerful thing.
Well, yes, okay, but the point is that it is not a thing of our, people imagine there is, I don't know, an elephant or something, mm-hmm. Or elephants are presumably not necessary objects. They happen to exist mm-hmm. as a result of kind of biological evolution and whatever else. But the thing is that in some sense that it is a different kind of thing to say, does plus exist? It's not like an elephant.
So a plus seems more fundamental, more basic than an elephant, yes. But
right.
You can imagine a world without plus or anything like it. Like, why do formal things that are discrete, that can be used to reason, have to exist? Or
then the question is, but the whole point is, computation, we can certainly imagine computation. That is, we can certainly say there is a formal system that we can construct abstractly in our minds that is computation, and that's the we can imagine it, right? Yeah. Now the question is that formal system, once we exist as observers embedded in that formal system, that's enough to have something which is like our universe.
Yeah.
And so then what you're kind of asking is why, I mean, the point is we definitely can imagine it. There's nothing that says that we're not saying that it's sort of inevitable that is a thing that we can imagine. We don't have to ask, does it exist? It is definitely something we can imagine. Mm-hmm. Now then we have this thing that is a formally constructible thing that we can imagine. And now we have to ask the question, given that formally constructible thing, what consequences does that, if we were to perceive that if we were embedded in that formally constructible thing, what would we perceive about the world? And we would say, we perceive that the world exists because we are seeing all of this mechanism of all these things happening. But that's something that is just a feature of, it's something where we are.
See, another way of asking this that I'm trying to get at, I understand why it feels like this Ruliad is necessary. Mm-hmm. But maybe it's just me being human, but it feels like then you should be able to, not us, but somehow step outside of the Ruliad. Like, what's outside the Ruliad?
Well, the Ruliad is all formal systems. So there's nothing.
But that's what a human would say.
I know that's what a human would say, because we're used to the idea that but the whole point is that by the time it's all possible formal systems, it's like it is all things you can imagine. But
all computations you can imagine, but like we don't.
Well, so the issue is, can we encode? Okay, so that's a fair question. Is it possible to encode all? I mean, is there something that isn't what we can represent formally?
Right.
That is.
Yeah.
Is there something that, and that's, I think, related to the hyper-Ruliad footnote, so to speak, of which I'm afraid that one of the things sort of interesting about this is, there has been some discussion of this in theology and things like that, but which I don't necessarily understand all of, but the key sort of new input is this idea that all possible formal systems. It's like, if you make a world, people say, well, you make a world in a particular way, with particular rules. But no, you don't do that. You can make a world that deals with all possible rules. And then merely by virtue of living in a particular place in that world, so to speak, we have the perception we have of what the world is like. Now, I have to say, it's sort of interesting because I wrote this piece about this, and I this philosophy stuff is not super easy, and as I'm talking to you about it, and I actually haven't. People have been interested in lots of different things we've been doing, but this "why does the universe exist" has been, I would say, one of the ones that you would think people will be most interested in. But actually, I think they're just like, oh, that's just something complicated. Yeah. So I haven't explained it as much as I've explained a bunch of other things. And I have to say, I think I may be missing a couple of pieces of that argument that would be so. It's kind of
your conscious being is computationally bounded, so you're missing.
Indeed,
having written quite a few articles yourself, you're now missing some of the pieces.
Yes, right.
That's the limitation of being human.
Right. One of the consequences of this why the universe exists thing, and this kind of concept of Rulliads and places in there representing our perception of the universe and so on. One of the weird consequences is, if the universe exists, mathematics must also exist. And that's a weird thing, because mathematics, people have been very confused, including me, have been very confused about the question of kind of what is the foundation of mathematics? What kind of a thing is mathematics? Is mathematics something where we just write down axioms like Euclid did for geometry, and we just build the structure, and we could have written down different axioms and we'd have a different structure? Or is it something that has a more fundamental sort of truth to it? And I have to say, this is one of these cases where I've long believed that mathematics has a great deal of arbitrariness to it, that there are particular axioms that kind of got written down by the Babylonians, and that's what we've ended up with, the mathematics that we have. And I have to say, actually, my wife has been telling me for 25 years, she's a mathematician, she's been telling me, you're wrong about the foundations of mathematics. And I'm like, no, I know what I'm talking about. And finally, she's much more right than I've been. So it's one of the.
So I mean, her sense and your sense, are we just? So this is to the question of mathematics. Are we just kind of on a trajectory through Rullial space, except in mathematics, through a trajectory, a certain kind of? And
I think that's partly the idea. So I think that the notion is this. So 100 years ago, a little bit more than 100 years ago, well, people have been doing mathematics for ages. But then in the late 1800s, people decided to try and formalize mathematics and say, it is mathematics is, we're going to break it down. We're going to make it like logic. We're going to make it out of sort of fundamental primitives. And that was people like Frege and Peano and Hilbert and so on. And they kind of got this idea of, let's do kind of Euclid, but even better. Let's just make everything just in terms of this sort of symbolic axioms, and then build up mathematics from that. And that, they thought at the time, as soon as they get these symbolic axioms, that they made the same mistake, the kind of computational irreducibility mistake. They thought, as soon as we've written down the axioms, then we'll just have a machine, kind of a super mathematica, so to speak, that can just grind out all true theorems of mathematics. That got exploded by Gödel's theorem, which is basically the story of computational irreducibility. It's that even though you know those underlying rules, you can't deduce all the consequences in any finite way. And so that was, but now the question is, okay, so they broke mathematics down into these axioms, and they say, now you build up from that. So what I'm increasingly coming to realize is that's similar to saying, let's take a gas and break it down into molecules. There's gas laws that are the large-scale structure and so on that we humans are familiar with, and then there's the underlying molecular dynamics. And I think that the axiomatic level of mathematics, which we can access with automated theorem proving and proof assistance and these kinds of things, that's the molecular dynamics of mathematics. And occasionally we see through to that molecular dynamics. We see undecidability, we see other things like this. One of the things I've always found very mysterious is that Gödel's theorem shows that there are sort of things which cannot be finitely proved in mathematics. There are proofs of arbitrary length, infinite length proofs that you might need. But in practical mathematics, mathematicians don't typically run into this. They just happily go along doing their mathematics. And I think what's actually happening is that what they're doing is they're looking at this. They are essentially observers in metamathematical space, and they are picking a reference frame in metamathematical space, and they are computationally bounded observers in metamathematical space, which is causing them to deduce that the laws of mathematics and the laws of mathematics, like the laws of fluid mechanics, are much more understandable than this underlying molecular dynamics. And so what gets really bizarre is thinking about kind of the analogy between metamathematics, this idea of you exist in this kind of in this sort of space of possible, in this kind of mathematical space where the individual kind of points in the mathematical space are statements in mathematics, and they're connected by proofs, where one statement, you take a couple of different statements, you can use those to prove some other statement, and you've got this whole network of proofs. That's the kind of causal network of mathematics, of what can prove what, and so on. And you can say at any moment in the history of a mathematician, of a single mathematical consciousness, you are in a single kind of slice of this kind of metamathematical space. You know a certain set of mathematical statements. You can then deduce with proofs, you can deduce other ones, and so on. You're kind of gradually moving through metamathematical space. And so it's kind of the view is that the reason that mathematicians perceive mathematics to have the sort of integrity and lack of kind of undecidability and so on that they do is because they, like we as observers of the physical universe, we have these limitations associated with computational boundedness, single thread of time, consciousness limitations, basically, that the same thing is true of mathematicians perceiving sort of metamathematical space. And so what's happening is that when you look at, if you look at one of these formalized mathematics systems, something like, Pythagoras' theorem, it'll take, maybe 10,000 individual little steps to prove Pythagoras' theorem. And one of the bizarre things that's a sort of an empirical fact that I'm trying to understand a little bit better, if you look at different if you look at different formalized mathematics systems, they actually have different axioms underneath, but they can all prove Pythagoras' theorem. And so, in other words, it's a little bit like what happens with gases. We can have air molecules, we can have water molecules, but they still have fluid dynamics. Both of them have fluid dynamics. And so similarly, at the level that mathematicians care about mathematics, it's way above the molecular dynamics, so to speak. And there are all kinds of weird things. Like, for example, one thing I was realizing recently is the quantum theory of mathematics. That's a very bizarre idea. But basically, when you prove what is, a proof is, you've got one statement in mathematics, you go through other statements, you eventually get to a statement you're trying to prove, for example. That's a path in metamathematical space. And that's a single path. A single proof is a single path. But you can imagine there are other proofs of the same result. They're a bundle of proofs. There's this whole set of possible proof paths.
You could think of it as branching, similar to the quantum mechanics model that you were talking about.
Exactly. And
then there's some invariants that you can formalize in the same way that you can for the quantum mechanical.
Right. So the question is in proof space, as you start thinking about multiple proofs, are there analogs of, for example, destructive interference of multiple proofs? Right. So here's a bizarre idea that's just a couple of days old, so not yet fully formed. But as you try and do that, when you have two different proofs, it's like two photons going in different directions. You have two proofs which at an intermediate stage are incompatible. And that's kind of like destructive interference.
Is it possible for this to instruct the engineering of automated proof systems?
Absolutely. As a practical matter, this whole question, in fact, Jonathan Gorard has a nice heuristic for automated theorem provers that's based on our physics project that is looking for essentially using energy. In our models, energy is kind of the level of activity in this hypergraph. And so there's sort of a heuristic for automated theorem proving about how do you pick which path to go down that is based on essentially physics. And the thing that gets interesting about this is the way that one can sort of have the interplay between, like, for example, a black hole. What is a black hole in metamathematics? So the answer is, what is a black hole in physics? A black hole in physics is where, in the simplest form of black hole, time ends. That is all, everything is crunched down to the space-time singularity, and everything just ends up at that singularity. So in our models, and that's a little hard to understand in general relativity with continuous mathematics and what does the singularity look like. In our models, it's something very pragmatic. It's just you're applying these rules, time is moving forward, and then there comes a moment where no rules apply. So time stops. It's kind of like the universe dies. Nothing happens in the universe anymore. Well, in mathematics, that's a decidable theory. That's a theory. So theories which have undecidability, which are things like arithmetic, set theory, all the serious models, theories in mathematics, they all have the feature that there are proofs of arbitrarily long length. In something like Boolean algebra, which is a decidable theory, there are, any question in Boolean algebra, you can just go crunch, 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 and in a known number of steps, you can answer it. Satisfiability, might be hard, but it's still a bounded number of steps to answer any satisfiability problem. And so that's the notion of a black hole in physics where time stops. That's that's analogous to in mathematics where there aren't infinite length proofs. When in physics, you can wander around the universe forever if you don't run into a black hole. If you run into a black hole and time stops, you're done. And it's the same thing in mathematics between decidable theories and undecidable theories. So that's an example. And I think we're sort of the attempt to understand. So another question is kind of what is the general relativity of metamathematics? What is the bulk theory of metamathematics? So in the literature of mathematics, there are about 3 million theorems that people have published. And those represent, it's kind of on this, it's like on the Earth, we would be, we've put cities in particular places on the Earth, but yet there is ultimately, we know the Earth is roughly spherical and there's an underlying space. And we could just talk about, the world of space in terms of where our cities happen to be, but there's actually an underlying space. And so the question is, what's that for metamathematics? And as we kind of explore what is, for example, for mathematics, which is always likes taking sort of abstract limits. So an obvious abstract limit for mathematics to take is the limit of the future of mathematics. That is, what will be, the ultimate structure of mathematics. And one of the things that's an empirical observation about mathematics that's quite interesting is that a lot of theories in one area of mathematics, algebraic geometry or something, they play into another area of mathematics. The same kind of fundamental construct seem to occur in very different areas of mathematics. And that's structurally captured a bit with category theory and things like that. But I think that there's probably an understanding of this metamathematical space that will explain why different areas of mathematics ultimately sort of map into the same thing. And I mean, my little challenge to myself is what's time dilation in metamathematics? In other words, as you move around in this mathematical space of possible statements, how does that moving around? It's basically what's happening is that as you move around in the space of mathematical statements, it's like you're changing from algebra to geometry to whatever else. And you're trying to prove the same theorem. But if you keep on moving to these different places, it's slower to prove that theorem because you keep on having to translate what you're doing back to where you started from. And that's kind of the beginnings of the analog of time dilation in metamathematics.
Plus, there's probably fractional dimensions in this space as well.
Oh, this space is a very messy space. This space is much messier than physical space. I mean, even in the models of physics, physical space is very tame compared to branchial space and rulal space. I mean, the mathematical structure, branchial space is probably more like Hilbert space, but it's a rather complicated Hilbert space. And rulal space is more like this weird infinity groupoid story of growth and decay. And I can explain that a little bit because in metamathematical space, a path in metamathematical space is a path between two statements is a way to get by proofs, way to find a proof that goes from one statement to another. And so one of the things you can think about is between statements, you've got proofs. And they are paths between statements. Okay, so now you can go to the next level and you can ask, what about a mapping from one proof to another? And so that's in category theory, that's kind of a higher category notion of higher categories where you're mapping not just between objects, but you're mapping between the mappings between objects and so on. And so you can keep doing that. You can keep saying higher order proofs. I want mappings between proofs and so on. And that limiting structure, oh, by the way, one thing that's very interesting is imagine in proof space, you've got these two proofs. And the question is, what is the topology of proof space? In other words, if you take these two paths, can you continuously deform them into each other? Or is there some big hole in the middle that prevents you from continuously deforming them one into the other? It's kind of like, when you think about some puzzle, for example, you're moving pieces around on some puzzle, and you can think about the space of possible states of the puzzle, and you can make this graph that shows from one state of the puzzle to another state of the puzzle and so on. And sometimes you can easily get from one state to any other state, but sometimes there'll be a hole in that space. And there'll be, you always have to go around this circuitous route to get from here to there. There won't be any direct way. That's kind of a question of whether there's sort of an obstruction in the space. And so the question is, in proof space, what does it mean if there's an obstruction in proof space?
Yeah, I don't even know what an obstruction means in proof space, because for it to be an obstruction, it should be reachable some other way from some other place, right?
Well,
so this is like an unreachable part of the graph.
No, it's not just an unreachable part. It's a part where there are paths that go one way, there are paths that go the other way. And this question of homotopy in mathematics is this question, can you continuously deform, from one path to another path? Or do you have to go in a jump, so to speak? So, So it's like if you're going around a sphere, for example, if you're going around a cylinder or something, you can wind around one way, and there are paths where you can easily deform one path into another because it's just sort of sitting on the same side of the cylinder. But when you've got something that winds all the way around a cylinder, you can't continuously deform that down to a point because it's stuck, wrapped around.
Well, my intuition about proof space is you should be able to deform it. I mean, because then otherwise it doesn't even make sense. Because if the topology matters of the way you move about the space, then I don't even know what that means.
Well, what it would mean is that you would have one way of doing a proof of something over here in algebra, and another way of doing a proof of something over here in geometry, and there would not be an intermediate way to map between those proofs.
But how would that be possible if they start at the same place and end at the same place?
Well, it's the same thing as we've got points on if we've got paths on a cylinder.
Now, I understand how it works in physical space, but it just doesn't, it feels like proof space shouldn't have that. I'm
not sure. I don't know. We'll know very soon because we get to do some experiments. This is the great thing about this stuff, is that, in fact, I'm in the next few days, I hope to do a bunch of experiments on this. So
you're playing with like proofs in this kind of space?
Yes.